Avengers! Assemble.
The objective of this project is to program an industrial machine with given requirements with Arduino and PLC ladder diagram. The machine being designed is an industrial machine for the quality control process of a battery's production system.
Now, for the PLC input, we have a normally open start push button, which represents the push button that turns on the motor, and the normally closed stop push button, which represents the push button that turns off the motor. Also, we have a normally closed load cell, which is connected to the load cell, along with two normally open photoelectric switches, P1 and P2, where P1 works with the defected batteries and P2 works with the non-defected batteries. For the PLC output, we have the motor, which represents the conveyor belt, the gate solenoid drive, which represents the gate solenoid drive, along with the print defect, which represents the printer's DC motor, which works with the defected batteries, and the heat, which represents the palletizing solenoid, which works with the non-defected batteries. Now for the PLC simulation, if we press the start push button, the motor will be turned on. It will stay on since it is latched, and if we press the stop push button, it will turn off. Now for the load cell emits a value of 2 volts for a non-defected battery and any other value for a defected battery. Now when a battery is defected, the gate solenoid is triggered and turned on so that the defected battery could change trajectory. When that happens, the photoelectric switch P1 is turned on in order for the printer to print defect on the defected batteries. Now if the battery is not defected, it will pass through photoelectric switch P2, which is a counter. It will pass, 4 batteries shall pass. This is the first one, the second, the third. Now on the fourth battery, when the fourth battery passes, the battery counter will reset, and also it will trigger a 2-second off delay timer, which will activate the heat, which will allow the wrapping to wrap along the non-defected batteries as it will be represented right now. And the system will repeat itself.
To simulate the last stage of the machine and have it controlled via Arduino, we consider that photoelectric switch P2 is replaced by the parallax ultrasound sensor, and the palletizing system is controlled using the micro servo motor. Here is a representation of the Arduino circuit connections. Starting with the parallax ultrasonic sensor, this sensor's pin called SIG can send and receive signals. The SIG pin starts off as an output pin. It then sends signals for 10 microseconds. Then it is put as an input in order for it to wait for the signals to come back to the sensor. The sensor function then returns the time the signal took to leave the sensor and bounce off the battery and then come back to the sensor in microseconds. After that, the time is converted into centimeters based on the fact that the speed of sound is 29 microseconds per centimeter. So the time of travel is divided by 29 and then divided by 2 to get the distance between the sensor and the battery only. If the distance read is below 5 centimeters, the system will increment the number of batteries by 1 until reaching 4 batteries. After that, the servo will rotate from its neutral position, which is 90 degrees, to 180 degrees. The delay function will be used to delay the time between each degree the servo motor rotates. Based on that, the greater the delay, the slower the servo is, and vice versa. After reaching 180 degrees, the servo will wait for 1 second and then go back to its neutral position using the same procedure. 2 push buttons will act as triggers in the system. Here we are going to discuss the plus push button, which is responsible for increasing the speed of the servo, so the minus push button does the exact opposite. Once the push button is pressed, it will trigger the pin and increase the speed, which also means decrease the delay function, which was mentioned in the previous slide. But if the speed is already at maximum, then it will do nothing. And likewise for the minus push button, if the speed is at minimum, then it will also do nothing. After that, the LED indicator function will be called to recognize the new speed and display it. small observation of how the 7-segment LED indicator works. For example, if we want to display the number 3, we set the pins on the LED indicator A, B, C, D, and G as high, and the rest we set as low.
The selection of the sensor and the DC motor. The load cell strain gauge is usually a Wheatstone bridge configuration. The representation of the Wheatstone bridge is as such. The voltage output and the change in R1, which is the change in weight, is the following equations, and the gain is G equal to, since in our case it is a metallic load cell. The load cell chosen is mini load cell 100G straight bar, which is shown in the figure below. The manufacturer is Spark Fan Electronics, and its data sheet is hyperlinked in our report. The output of the voltage for a 20-gram battery is 0.27 millivolt, which goes to the PLC. Any voltage other than that will let the solenoid gate to open, which will divert the path of the battery. Now, since 0.27 is a small voltage, a non-inverting op-amp will be used to amplify 0.27 millivolt to 2 volts. An alternative to the load cell would be a piezoresistive sensor, which is shown in the figure below. To compare both, we found several disadvantages and advantages. For instance, the load cell is very accurate and calibrated by the manufacturer, but big in size, whereas the piezoresistive is thin, flexible, customizable, but less accurate. For the DC motor, using the specs given, the parameters of the DC motor are as follows. Assume VA equal 42 volts. Using the no-load speed and the stall torque as 2 point, we plotted the following graph. Therefore, we got the following values of Km, Kt, Ke, Ra, Tf, and maximum efficiency. The power output of the whole system as function of the motor torque, we get from the following graph a maximum power output of 34.57 watt and a motor torque of 0.074 Newton meter. Next, the motor power as function of motor torque. From this graph, we get maximum power output of system, which is 35.92 watt with the motor torque of 0.073 Newton meter.